We are now going to look at the Hoffman elimination of a primary amine to give an alkene, and it's very specific about the type of alkenes that you're making here. The alkenes that you're going to make as your major products are the ones that are the least stable. So Hoffman eliminations are used to make these harder to make alkenes preferentially. So hopefully from everything you've been studying this chapter, you know how to make primary amines. We're just going to use this one. And it is important that you use a primary amine. What you do with it initially is you're going to use excess methyl iodide. That will be your first step on the arrow. And once you've had the chance to let that run its course, you'll do the second step of this reaction, which is to add silver 1 oxide and water. So this really is a two-step process. We're going to go through the first step. It's very simple chemistry that you should be very familiar with. All it is SN2 substitution repeated 3 times. So let's go through this. Just to remind you how SN2 substitution works with a very specific nucleophile and a very specific substrate. Your substrate here is the methyl iodide. You have a very good leaving group in the iodide. When it kicks off, you'll have a very weak base, and that is a good leaving group. The nitrogen here can act as a nucleophile because it is an electron pair donor, and it does do this SN2 substitution. So it comes in and does this backside attack, and at the same time the iodine kicks out, which will leave you with this chemical species. Now, probably what will happen at this point is that one of your other amines in solution will act as a base and remove one of these 2 protons. So here comes your amine, removes the proton, give electrons back, and now instead of a primary amine, you have a secondary amine. And we've talked about this. This is a reaction you can't stop. It just keeps going. And that's why these aren't very good reactions for making more complicated amines, because you can't isolate any one of these products. So you would also have your new protonated amine and the iodide. Those are spectators, but they're present in the solution. This amine will then react with some more methyl iodide. And the nitrogen acts as the nucleophile, kick the halogen out. Well, you have another one of your solvent molecules around, some more primary amine or maybe a different amine. I'm just going to use the one we started with, but it could be a different amine. It'll come in here and remove the proton, give electrons back. So now we're going to have a tertiary amine. This is the problem, it just keeps going. Well, if we have more methyl iodide, you can do it again. This is why we want excess methyl iodide present in the solution. So you go through this process yet again. It adds as the nucleophile, kick your leaving group out. Now this nitrogen's got a problem. There is no more proton, so you can't get rid of anything. This is where you are. So you basically have done SN2 substitution 3 times and you're stuck. You're a quaternary ammonium salt. You're stuck. This is when the silver oxide is added in water. The reason you add the silver oxide is so that you can do some inorganic chemistry and do a displacement reaction. What we're basically going to do is swap out the anions. And it's very important that you use silver. I'm going to kind of remind you why. But way back when in general chemistry you studied solubility rules. And you learned something about halides. There are a few cations that when a halide is paired up with it, they become insoluble. And silver 1 is one of those. There aren't very many. The others would be lead and mercury 1. Nobody wants to really work with lead or mercury, so you try silver. It's a little safer. So we use the silver oxide, and it's going to basically swap out the anion. So you're going to replace the iodide with the hydroxide by doing this. And you're going to get a silver iodide precipitate, and it comes right out of the water solution and you can filter it out. This is how you get rid of the iodide in the solution. It goes away. Alright. Now I'm going to redraw the carbon skeleton on top so that you can see exactly what we have here. It's just not letting me draw, sorry. I drew out all the hydrogens that might be interesting to us. Now the reason we used methyl iodide was for a couple of reasons. Number one, by going through this substitution 3 times, we've got a nitrogen with a positive charge. It's now a really good leaving group because if it leaves, this carbon nitrogen bond right here that I'm going to redraw in red a little bit, that pair of electrons will go to nitrogen. And so you'd have a really good leaving group there. And what we're basically going to be looking at doing here is an E2 elimination, because you've got hydroxide. It's a strong base. And that's a great leaving group right there. So if that's a good leaving group, we want to look at removing a proton on a carbon adjacent to the leaving group. Now, by using methyl groups, there are no carbons adjacent to this leaving group. You could not do an elimination to any one of these carbons since there is no carbon adjacent. That's why we use methyl iodide. You can't do an elimination at those locations. But these 2 carbons right here do have protons, and they are adjacent to this really good leaving group. Now one of the positions is better than the other. This is why we call it the Hoffman elimination. And I know in class I would have shown you a model using a Newman projection. But these are very important that we take a look at the most stable conformation along each of these carbon-carbon bonds. So we can look at this one, or we could look at this one. So you want to look at the most favorable conformation for an E2 elimination. If you remember with E2 eliminations, your hydrogen and your leaving group have to be anticoplanar to one another in order for the stereochemistry to be correct when this leaves. So let's look at the 2 most stable conformations along those 2 different carbon-carbon bonds. First off, I'm going to look at the one in green. Okay? So on my front carbon, we'll say it's the one on the left back here. Notice that it has 2 hydrogens and a methyl group. And on the back carbon, you have a hydrogen, a methyl group, and that big old nitrogen group with 3 methyl groups. So the nitrogen with the 3 methyl groups needs to be anticoplanar to the biggest group on the front. So this is where the nitrogen has to go. And then you have a methyl group that can go in either of these 2 positions, and a hydrogen. Now, remember what must be true for an E2 elimination. The leaving group, whoops, I didn't put the positive charge on that guy. The leaving group needs to be anticoplanar to a hydrogen. It is not anticoplanar to the 2 hydrogens on the adjacent group in the most stable conformation. I'm not saying that you couldn't rotate it, but if you do so, you would not be in the most stable conformation. Now let's look at the carbon-carbon bond that I've shown here in blue. On the front carbon, you have a hydrogen, an ethyl group, and this nitrogen with the 3 methyl groups. On the other carbon, you have 3 hydrogens. This is the most stable conformation along the carbon-carbon bond that I've drawn here in blue. So let's take a look at these 2. So the carbon-carbon bond that I've circled there in green, this is the most stable conformation. The leaving group is not anticoplanar to one of the 2 hydrogens on that front carbon. But if we look at the carbon-carbon bond here in blue, and its most stable conformation, we do have our leaving group anticoplanar to a hydrogen. So this is much more favorable for reaction because of the conformation the molecule prefers to be in. Here we have the appropriate groups anticoplanar to each other so that when the p orbitals form, they are in the same plane and you can have that double bond. So what occurs here, if we're just talking about mechanism, is that this hydroxide will come in here and remove one of those protons. The carbon-hydrogen bond breaks, and this pair of electrons is used to make the carbon-carbon double bond, and at the same time, the leaving group departs. That's what's happening mechanistically. I'm also going to show that same thing from the Newman projection. So you have your hydroxide. And it will come in here and remove the proton. This pair of electrons will make the carbon-carbon double bond, and your leaving group kicks out. This is all in the same plane, which is what is required for an E2 elimination. And by doing so, you'll be able to make your products. So we are going to make, as you can see by doing this at the blue position, the carbon-carbon bond there in blue, we'll be able to make a monosubstituted alkene. If you'd done it from the carbon-carbon bond there in green, you'd have a disubstituted. You'd have cis and trans. So what we're going to get as our major product in this particular case is the less substituted double bond. The minor products will be trans and cis due to the stereochemistry. And then you would also produce some water. That's also going to be produced. And your amine. Those are now neutral and happy to just sit out there in solution and not do anything else. So if you want to make, again, these alkenes that are less stable, less substituted, Hoffman elimination is the best way to do that.